class. Okay, so we're going to talk about electrical energy. So before we talked about electric potential, and now we're talking about electric potential energy. And it's unfortunate these the terms are so similar, but they mean different things. They're related, but think electric potential is measured in volts. Let's write that down. So potential is in volts, and energy is in joules. So again, if you pay attention to the units, you shouldn't be confused about which thing we're actually talking about. Okay, now I actually introduced this idea of electric energy before, where I had to kind of just write down the answer. So we looked at a situation where we have, say, Q1, which is fixed, and Q2 is going to move from, say, A to B. And we say that Q2, if we just look at Q2 as like our system and Q1 is some external thing, then Q2 has potential energy because of the electric field of Q1. And so to calculate the change in potential energy, we have to look at the work as we move from A to B. That's how potential energy is defined. The problem is that the force depends on the distance, so as we're moving, the distance is changing. So we don't have a constant force here. So in an algebra-based class, well, what can you do? I just have to write down the answer. So the work done moving from A to B, basically think of the force times the distance, but I'm just going to write down the answer. Which kind of, why do we start with a negative and then a positive term? Well, it's mainly because if we were calculating the work using calculus, this is how it would naturally fall out. But it turns out to be a convenient way to do it because the work, this is a work going from A to B, and remember work is equal to minus, or the change in potential energy is minus the work. So the change in potential energy, that's why it's final minus initial, so we have UB minus UA is equal to minus the work from A to B. So let's use that. So we have the potential energy at B minus the potential energy at A is equal to minus the work. So minus this, and this would be a positive term. And then okay, so that's how we define changes in potential energy, just based on Coulomb's law. We're talking about this electrostatic case where the forces involved are conservative, and therefore we can define the potential energy function in the first place. Now, here we can only talk about changes. So it's always good to compare things to gravity, where we can talk about the change in potential energy, like say as I lift up this eraser. So not much, the eraser is very light, but there was a change in potential energy. We usually don't talk about it that way. What we do in the case of gravity, like especially if we're talking about gravity near the Earth's surface, let's just set this as say 0. So right now on the marker we can just say that it has 0 potential energy, and then we lift this up and now it has a certain amount of potential energy, which has got to be a positive number because if I drop it, it gained speed. So it gained kinetic energy, so it had to have this stored energy, which was potential. Like the work I went into it, the work I exerted, lifting it up, that energy is stored, we can think of it that way. And then it converts into kinetic. So yeah, it does involve a change, but we set this reference level of 0. But when it comes to, if we go back to gravity, potential energy was simple mgh, and it's very easy to just set h equals 0, and then u is going to be 0. And it's a little more difficult when it comes to electrostatics, because we can't set any of these terms equal to 0 by plugging in some value for r. We can't, we definitely don't want to set r equals 0, then this term would become infinite. And so, in order to set let's say we want to set a reference level to be 0, we could, if we want to set one of these terms equal to 0, basically we'd want to make this r to be as large as possible. We talked about the point at infinity, where r is big enough so that this term is essentially 0. And then we can just define a potential energy function. So this is, if you just see a potential energy as a function, not a change in potential energy, then you know that there is a reference level. And in this case, you can see when r is infinity, then the potential energy is 0. So in practical terms, r would just have to be big enough so that one of these terms would be insignificant. Okay, so that's potential energy. Electrostatic potential energy. Now, that's due to the interaction of these two particles, and before we're kind of looking at, say this particle is fixed and this particle is moving around. And so our system in that case was just Q2. And Q1 is some fixed external thing, but a lot of times, most of the time, we want to consider this pair of, the combination of charges. What if that was our system? Then we can say the energy is stored in the system without really specifying which particle has the energy. So before, it's kind of like the case for gravity, where the Earth is this external thing, and this marker is in a gravitational field. And so, we're only focusing on the mass itself. So that's what we did before. We had one fixed particle just to create an electric field, and then the other particle can move around in that field. But more generally, these particles can interact with each other. So if you have Q1 and Q2, if we treat that as our system, then we can say that there's a certain potential energy between them without specifying where that energy is. And so basically, let's say these are opposite charges. If we release them, they're going to come together, and so they're both going to gain kinetic energy. And so we can just talk about the energy of interaction. And it doesn't belong to either particle or any particular part of the system. Just this combination of particles has a certain amount of potential energy. And what if we have more than, say we have more than one charge, or more than two charges. So let's say we had a charge distribution. Let's keep it simple. Let's say we have three charges, Q1, Q2, and Q3. So they'll naturally form a triangle. And there's distances between them. So let's label this R12, the difference between, or the distance between charges Q1 and Q2. Similarly, we'll call this R23, and this is R13. Okay, so our goal is, we want to know how much energy is stored in this system, and the idea is we have to think of it, how much energy would it take to build this system? So, well, by building, we don't mean build it from scratch, because these charges existed. But say they started out very far away where they're not really interacting with each other, and then we want to bring them together. Let's just say, for simplicity, say they're all positive charges, so they're fighting us if we try to bring them together. So we'd have to exert energy to force them into this configuration. And so we have to do work, and whatever work we put into it, that's the stored energy in this system. So our goal is, let's calculate how much work it's going to take to create this, where we assume that they all start out very far away from each other. And I also want to assume that they start out far away from where they're eventually going to end up, just to make things simple. So imagine all these particles are very far away from, these locations. And let's bring them in one at a time. And the question is, how much energy does it take to bring Q1 from really far away to this location? So we'll start out just looking at charge 1. The work that we'd have to put into it is 0. And the reason why is, remember, charge 2 and 3 are still nowhere near this board. They're very far away. And so even when Q1 is over here, it's not going to be interacting with Q2 and Q3 in any significant way. And so Q1, we still have to move it, but that doesn't require any energy at all because of inertia. We're just talking about electric potential energy. There's no gravity involved or anything like that. So say Q1 started far away. If you just gave it a little nudge to get it moving, its inertia is just going to carry it all the way to its, so you want it to stop here, then you stop it when it gets here. But it doesn't really take any energy to bring in Q1. Okay, what if we bring in charge 2? Well, now there's going to be work required. Because charge 2, once it gets close to Q1, they're going to start pushing off each other. Q1 is fixed. Now we're going to have to force Q2 into that location. And the work required is just that potential energy function. So this is how much work we'd have to put into bringing Q2 in. It's going to interact with charge 1. And so again, we know this is how much work it would take to do this, because this energy, it would be stored in, that would be the potential energy that the system would have if we just had charges Q1 and Q2. Okay, so now Q1 and Q2 are fixed. Let's bring in Q3. So to bring in charge 3, it's going to be fighting against both charges 1 and 2. So we're going to have an interaction between 1 and 3. And there's also going to be an interaction between 2 and 3. Okay. And now if you want to know the total amount of energy stored in this configuration, we add up these 3 terms. So we start with 0, and then we have I'm going to write this over here. Let's say for 3 charges. Hopefully there's room. Okay. So basically we just, we have this term, Ke Q1 Q2 over R12. Then we add this one, so 2 more terms. So if there's 3 charges, that would be the energy of the configuration. Now, what if we brought a 4th charge in? I'm not going to write it down. You think, like, how many terms would we have overall if we brought in a 4th term, or 4th charge? And so again, we already have the energy it took to build this, but if we brought in a Q4, that Q4 would interact with Q1, Q2, and Q3, so we'd have 3 additional terms. Basically, we'd have a Q1, Q4, Q1. Or here, we can do Q1, Q4 over R14. And we'd have Q2, Q4 over R24, and we'd have a Q3, Q4 over R34. So you'd have 3 additional terms, or of course we'd have a K in front of each. But basically the idea is, when finding the energy of a configuration, you look at like all the pairs of charges, each one has one of those terms. So to start out with, let's make this an actual problem. Let's just make up some numbers. So I'm just trying to figure out where to write this, where we'll have room. Here, let's say Q1 is, say, 3.5 microcoulombs. Let's make Q2 negative. So Q1 and Q3 are positive, Q2 is negative. And to make things simpler, I'm running out of room. Let's just say R, let's say it's an equilateral triangle. We'll just make it up, say 1.4 meters. So like, how much energy is stored in this, or how much energy did it take to build this this configuration? Well, let's calculate this. Now, in this case, we have every term. I kind of made this a little bit easier, just to save room on writing mainly. But if all these R's are the same, we can factor a Ke over R, and then just look at these Q1, Q2, plus Q1, Q3, plus Q2, Q3. So we just factor out this common Ke over R. So let's do this. So we have 9 times 10 to the 9th Newton meters squared over Coulomb squared. That's Ke. We're dividing by 1.4 meters. And now we've got these charges. Now Q1 and Q2, I'm definitely going to run out of room here. So let me just write these numbers down. I want to just save space. I don't want to write like 3.5 times 4.1. So that number is negative 14.35. And then Q1 and Q3 is going to be a positive term. Let's do that. That's 16.8. And then Q2 and Q3 is going to be negative 19.68. I'm going to have to erase this picture. Here, let's redraw it over here. Q1, Q2, and Q3. and they're separated by some distance r, where r was 1.4 meters. Okay, so, well, now we've got a little more room. And so these products, Q1, Q2, they were in microcoulombs, so we have microcoulombs squared. And I want these in coulombs, so we can say 1 coulomb is 10 to the 6th power microcoulombs, and we have to square that conversion factor. So let's go through, actually one more thing. I'm going to say a joule is a Newton times a meter. And now let's just go through and check the units. So we have newtons times meters squared. Microcoulomb squared. Coulomb squared, and joules. So it's just going across the top. On the bottom we have coulomb squared, meters, microcoulombs squared, and then a newton and a meter. So again, just literally going across the bottom, just in order, but lining them up this way. So you can see everything cancels out, and we'll get our energy in joules. So now let's look at the actual numbers. Here we've got 19.68 and 14.35. That's 34.03. And 16.8 is the opposite sign. So let's subtract those. So in magnitude, this is 17.23, but more negative than positive. So that number is going to be 17.23, but overall it's going to be negative. And that's it on top. Okay, so I've got the number. I'm going to erase this. Okay, so on top we have 9 times 10 to the 9th, and then this number, which was minus 17.23. And then on the bottom, we have 1.4 times 10 to the 12th. So here we have 10 to the 6th, but it's squared, so it's 10 to the 12th. So if we clean this up a little bit, get our minus. I'm going to do 17.23 times 9. That's 155.07. And on the bottom, I'm going to write 1,400. So I did, it's 10 to the 9 over 10 to the 12. That's 10 to the 3rd on the bottom. So this would be 1,400 on the bottom. And now you can see that the energy in this configuration is minus 0.11 joules. So the energy of the configuration is negative, and that's because this negative charge here, basically there's going to be a repulsion between Q1 and Q3, but an attraction between Q1 and Q2, and an attraction between Q2 and Q3. So basically, it would not take any energy to put this together because they're mostly attracted to each other. So if you put them reasonably close together, they would come together on their own and form some configuration. They wouldn't come into this nice triangle on their own, but you'd have some help putting them in this configuration. And so the actual energy stored is negative in this case. Like, if you wanted to pull these apart, you would have to do work. So if you have like all positive charges, if you want to pull them apart, you do nothing, they just go. In this case, though, you'd have to, like, say you want to pull Q2 out of there. Or no, let's start out. Let's say we want to remove Q1. Well, Q3 is going to be helping you, but Q2 is going to be, pulling on it. And so, yeah, overall, it would take energy to kind of dismantle this triangle, to move these charges away from each other. So that's what that negative sign means. Now, you could have this for any number of charged particles, where you have a similar, this is just the formula for 3 charges. You could have 10 charges, but again, the number of pairs grows very quickly. So it probably won't go more than 3 particles, like on a quiz or a test, just because, like if you had if we added Q4, that would be an additional 3 terms. And then if we added Q5, well, that'd be an additional 5 terms. Once we have Q4, to bring in Q5, or no, that'd be an additional 4 terms for that. Like, the number kind of builds up pretty quickly. And so it's a lot of writing and a lot of calculations. But I think, the idea is the same. If you have 3 charges, you can, see we have these 3 pairs of interaction. Okay, so that's the energy of a charge distribution. Now, I want to talk about, I erased that formula. I'm going to write down this formula that I erased again. Let's kind of go back to the beginning, what we were talking about. Delete that. Actually, no, I'm going to erase this. I'm going to write something else. Here, what we had is this situation. Where we had, Q1 is fixed, and charge 2 is going to move from point A to point B, where the change in potential energy would be okay, so yeah, that's Q2, same charge. I initially wrote Q3, but it's 1 charge moving. And so this is the change in potential energy. And we can, let me be a little more specific. This would be UB, or no, sorry, that would be the work. So the change in potential energy, we'd have the opposite sign. And so what I wrote down initially was work, where this first term was negative, second is positive, but the change in potential energy is minus that. And again, the change, that's final minus initial, so this would be UB minus UA. So basically, we're not setting a reference level here. We're just looking at a change in potential energy. Now, why are we doing this? Well, I'm going to rewrite it here. I'll write it like this. Delta U, that would be UB minus UA. And what I'm going to do is I'm going to factor out this Q1. No, sorry, I'm going to factor out Q2. And then we have KE Q1 over RB minus KE Q1 over RA. Okay, so all I did is algebra here. But, why did we do this? And the answer is, remember the electric potential is KEQ over R. And so the reason we factored out Q2 is Q1 is fixed. So it creates an electric field that's going to be static. Q1's not moving. We're just looking at what happens as we move Q2 around. And we can see that, well, here, let's continue. Here we have Q2. And this is the potential due to charge 1 at position B. That's potential due to charge 1 at position A. And so we're seeing that in this particular case, if we move Q2 around, what we have is a change in potential energy is that charge times the change in potential due to this external field created by Q1. However, all electrical fields are created by charges. So we can say more generally, let's get rid of Q1. But let's say there is an electric field. So there has to be charges creating this electric field that Q2 is moving around in. Well, let's say we don't really care where that electric field came from. It just exists. In general, we can say that the change in potential energy is equal to the charge times the change in potential. So like if you have some charge moving around in an electric field, remember the electric field and potential are related. So there's an electric field, which you can think of as creating this changing potential region. So if you move, so this is the charge that's moving around in an external field. So this is how electric potential and electric potential energy are related. So this is a very important equation here. It's on the equation sheet. Delta U is Q delta V. So we got it by looking at this particular case where we have Q1. But again, say we're confined to this box. We can't see outside of this box. What we have is this charge moving around in an electric field that's coming from somewhere outside. And because of this electric field, remember the electric field is that change in potential over distance. And so, yeah, the potential has to be changing as we move away from this charge. And so, yeah, we found that this, this result, we're just looking at like the electric field of a single point charge, but it applies in general. So if we know what the potential looks like in some region, we don't have to necessarily know what's creating that potential. We just have to know that it exists. Okay, so a very important equation here. Now I want to do a problem I'm going to write this down. We've got delta U is Q delta V. Okay, so I want to do a problem. I'm going to draw this. Say we've got so I'm drawing some equipotentials. And let's say x equals 0 here. This is like 1, 2, 3, 4, 5. Actually, I think I need one more line. Like 0, 1 meter, 2 meter, 3, 4, 5. So they're all equally spaced. I just don't want to write them all down. Okay. And as far as voltage is concerned, let's say the electric field is 100 volts per meter. So we have an electric field with a magnitude of 100 volts per meter. And we have a particle, let's say we have a mass, just made up some numbers here. Say it's a very small particle, 4.5 micrograms. And we're going to fire it into this region with an electric field. This particle has a charge of minus 3.7 microcoulombs, and it has an initial velocity of 921 meters per second. So we're going to fire it into this region with an electric field, and eventually it's going to stop. So what that means, this is a negative charge. And so once it enters this region with an electric field, there's going to be a force on the charge, and we want the force on the charge to be to the left. And so the electric field is going to be have to be to the right. So remember, the force on a charge is, if it's a negative charge, the force is the opposite direction of the electric field. So if the electric field is to the right, once this negative charge enters that region, the force will be on the left. So it's going to slow down, and it's eventually going to stop. I want to know, how far is it going to go before it stops? And let's label this. Remember, we know that electric fields go from high potential to low potential. So let's just say that the potential here all the way at this end is 0, and it's 100 volts per meter, so this would be 100, 200, 3, 4. So it starts out at 600 volts over here. Okay, so kind of the setup part is mostly done. We have all the information we need. We just want to know how far this particle is going to go before it stops. And so what I'm going to do is I'm going to label this point A. So it's not in the electric field yet. We'll say this whole thing is done in a vacuum. So this is point A, and it's going to stop somewhere. I have no idea where, so I'm just going to pick some random spot in here and say B. Now we have this rather unfortunate situation here. Because here I wrote V equals 0. What is V? Is that velocity or voltage? Or, potential. And, well, this is a lowercase v. Obviously, these are uppercase v's. So to distinguish them, I'm going to write voltages with this little, line at the end. So, this is a velocity that's just a lowercase v. So I'm talking about electric potential. I'm going to just write V in a distinctive way, just because it's very easy to get those confused. Well, this is a unit I can here. Okay, so the approach we're going to take here, now there's actually two approaches that we could take. Now, these are equally spaced potential lines, so in this case, we're talking about a constant electric field. And one approach we could take, we know the strength of the electric field. We could say a force is equal to Q times E, and because the electric field is constant, we have a constant force. And so if we from Newton's second law, force is mass times acceleration. So the acceleration would be QE over m, which is constant. And because it's constant, we can use that kinematics that we learned back in 121. We had a whole chapter on kinematics in the case of constant acceleration, which in this case it happens to be a constant acceleration, but it might not always be. So let's not assume, or let's not do it that way, even though that's a perfectly valid way of doing it. So we could find the acceleration and then use. I guess it would be fairly straightforward to do that. We could use this equation. If you remember that all the way back from chapter 2 in 121. Yeah, it's like final velocity would be 0, that's its initial, the acceleration would be negative. We could solve for delta x, but we're not going to do that. Because the approach we're going to take is conservation of energy, which would work. And the reason we're doing that is two reasons. Well, one, we don't have to assume that the acceleration is constant to do it this way. So that's one advantage of conservation of energy. And the other reason we're doing it is just that's the topic we're talking about is energy. So why don't we use it? But yeah, the other way is perfectly valid as well. So conservation of energy, we see it that very simple, in a very simple way. Energy at point A equals energy at point B. Energy is conserved. We can put a point C, point D, whatever. The energy is always going to be the same. So we're assuming here that the only forces acting on this particle are electrical. So only electric forces, no gravity, no air resistance. If we had gravity, that would be another term to worry about. But again, this is actually a fairly realistic to assume gravity because this thing is moving, 900, that's almost a kilometer per second. And so it's not going to go all that far. And so we're talking about a very short time interval. Gravity is not going to have much of an effect. Air resistance could be a problem. So we'll assume we're doing this in a vacuum chamber. It would have to be a very big vacuum chamber because 6 meters. So you'd have to have a whole vacuum room basically. But leave that to the engineers to worry about building that. But yeah, so again, conservation of energy. And no air resistance, so this is valid. So the types of energy we have here are kinetic and electric potential energy. So at A we have kinetic energy. So we have kinetic energy at A. And let's say the potential energy at A. Now, at point B, we're assuming that it came to a rest. So there's no kinetic energy at point B. And so, yeah, this is it for conservation of energy. We have kinetic energy at A, potential energy at A, and potential energy at B. And let's solve for the kinetic energy, which I'm going to write as 1/2 m, and I'll write VA squared. So again, that's a lowercase v. So that would be the potential energy at B minus the potential energy at A, which would be Q times the potential at B minus the potential at A. Okay. Or we could write Q delta V. I'm just thinking it might have been better if I didn't set the 0 here. Let's fix it. Remember, potential, it's kind of arbitrary where you set your 0. Yeah, let's set this 0 here. Let's say the potential at A is 0. And then remember, the electric field goes from high potential to low potential. So over here, we'd have minus 600 volts. But yeah, that'll make things a little easier. Then we can just say Q times the potential at B. So we'll just set the potential at A equal to 0, even though that's not the lowest point of potential. Totally fine to do that. Okay, and what we want to do, let's solve for the potential at B. So potential at B. So basically we just divide by Q. So we have mass times the velocity at A squared over 2Q. So again, that's a velocity, that's a potential. And now let's plug in some numbers. So the mass is 4.5 micrograms. Kind of a, let's do this. And Q is 3.7 microcoulombs. minus that. So let's just put that minus sign in front. I mean, we know the potential at B is going to be negative because we're starting at 0 and going into negative numbers here. Oh, I forgot the 2. Let's redo this. Okay, so we've got minus. The mass, it's kind of unfortunate that, the SI unit is like the base unit's kilogram. So gram, that's kind of already has a prefix in front of it, but we'll deal with it. Okay, so now in the bottom we have 2Q. So 3.7 times 2 is 7.4. And basically these micros cancel each other out. Because this is times 10 to the minus 6 grams, times 10 to the minus 6 coulomb on the bottom. These 10 to the minus 6 cancel out. So we'll just ignore those. I do want to convert to kilograms. So 1 kilogram is 1,000 grams. Okay, and now we've got our velocity squared. That'd be 921 meters per second squared. So I'm going to write this off to the side. Remember, a joule is equal to a coulomb times a volt. And again, here, like energy in joules, charge in coulomb, potential in volts. So a joule is a coulomb volt. And a joule, we can write that as a Newton times a meter, where a Newton is a kilogram meter per second squared. So a Newton times a meter, that'd be a kilogram meter squared over second squared. So if we multiply by second squared, we can say coulomb times volt times second squared is equal to a kilogram times a meter squared. So we've got this kind of horrible looking thing here. But as long as we just go through slowly and carefully, it shouldn't give us too much of a problem, other than running out of space on the board. This recurring problem. So first I'm going to look at the units on top. The only thing I'm going to do is I'm going to ignore these micro because we have one on top, one on bottom. They're going to cancel. So just going across the top, I'm going to write gram. And then we have a kilogram. And then meters squared. I'm actually going to write it as meters squared instead of a meter times a meter. Coulomb, volt, and second squared. So gram, kilogram, meter squared, coulomb, volt, second squared. That looks good. Across the bottom we have a coulomb, then a gram. Then here we have second squared because that's, in the parentheses with the exponent. And then kilogram, meters squared, and that's it. So yeah, everything cancels out except for volts. So this actually does give us the potential in volts. Now we have to get the number. Let's do that in the one space of the board that we have left. So the potential at B is going to be minus. So here we have 4.5 times 921 squared. I believe that's all we have on the bottom, or on the top. And on the bottom we have 7,400. 7.4 times 10 to the third. And that would be the potential in volts. So let's do that. I do 921 squared first. That's 848,241 times 4.5. And then divided by 7,400. So what I'm getting is 516 volts. Minus 516 volts. Okay, so that would be the potential at point B where it stops. So actually I'm going to move point B. So again, remember this is 0, it's 100 volts per meter in magnitude, and it's going down. This is minus 100, 200, 3, 4. This is minus 500. So it's actually going to stop over here. So this would actually be point B, where the velocity at point B is 0. And that occurs at minus 516 volts. And so the actual distance that this particle would travel before coming to rest, that'd be 5.16 meters. It's 100 volts per meter, so 516 volts, that'd be 5.16 meters. So that's how far it would go. So it's slowing down the whole time. That's where it stops, and then it would launch back. And it would reach speed, point A with a speed of 921 meters per second again, just from conservation of energy. So, yeah, that's a good way to approach these problems as conservation of energy. The other approach, just using Newton's laws, that would work in this case, but only because we have a constant electric field, which means a constant force and then a constant acceleration. All right, so I think this is a good place to stop. Yeah, I think we'll stop it here. Next topic we're going to talk about is capacitors, and then I'll actually finish that chapter, and then we have one more chapter to go in this section. But we'll stop this one here.